Understanding black holes is challenging because it involves imagining a non-static fabric of spacetime. The fabric of spacetime, where all events in the universe take place, is flexible and can be bent and curved by the masses moving upon it. If the stage you're on bends and warps, and you try to move on it, what happens? You'll be forced to move in the direction the stage is bending. Or, in the immortal words of physicist John Archibald Wheeler, matter tells spacetime how to curve, and spacetime tells matter how to move. Now, there are two ways to understand black holes within this framework. The first is to understand what black holes are as typical physical objects, like other celestial bodies. When stars about 20 times or more the size of the Sun run out of fuel, they undergo a massive explosion called a supernova, ejecting about 85% of their mass into space, leaving only the core behind. This core can still have a mass of millions, trillions, or even quadrillions of pounds. But without fuel to sustain fusion, there's no force left to counteract its collapse. If the remaining core is at least 3 solar masses, this mass begins to collapse at incredible speed onto itself, ultimately compressing an enormous mass into a minuscule volume. Consider how small the volume of this object becomes. Before turning into a black hole, a star 20 times the mass of the Sun typically has a radius much larger than the Sun's, thus having roughly the same density as the Sun. But after its death, this core of at least 3 solar masses doesn't expand to hundreds of thousands of miles, but instead collapses into just a few miles. For instance, the black hole GROJ1655, which is 5.4 times the mass of the Sun, has a radius of only 10 miles. Yes, just 10 miles. To visualize 10 miles more easily, imagine squeezing 5 to 6 suns into this tiny space. When you compress such a vast amount of mass into such a small volume, the fabric of space-time bends to an absurd degree. This leads us to the second way of understanding black holes, not as stellar objects like stars or planets, but as a tear in the fabric of space-time, almost like a piece of the universe has been ripped out. You could think of it as an anomaly in space-time. And now, you're about to be the first person to enter this anomaly. What do you think will happen to you? To understand this, we must divide what we call a black hole into 2 parts. First, there's the physical singularity believed to be at the center of the black hole, the infinitely small point where the star's core collapsed. We'll get to why it's believed to exist shortly. Second, there's what you see from the outside, or rather, what you don't see. A pitch-black sphere, which we call the event horizon. Let's look closer at the event horizon since we'll pass through it first. Normally, we have 3 dimensions of space to move freely, up-down, left-right, forward-backward. But near black holes, space-time bends so dramatically that all these dimensions point towards the singularity at the center. So, once inside a black hole, the only place you can reach is its center. Think of it like this. Is there any way to escape tomorrow? No, tomorrow will come and be experienced regardless. It's a thermodynamic necessity. In a black hole, these 3 spatial dimensions bend so much that they all point to the same place, the singularity. Hence, whether you go left, up, or back, it doesn't matter. These directions all lead you to the singularity, just as you can't escape tomorrow. Therefore, even photons moving at light speed can escape from a black hole. That's why, from outside, the event horizon looks like a dark void because no light from within can reach our eyes or telescopes. For example, when you reach about 1.5 times the radius of the black hole, you enter a region called the photon sphere, where photons, which normally must take the shortest path between 2 points, orbit around the black hole. Yes, the space-time is so warped that light can orbit like a planet around a star. Upon reaching this area, if you pause and look one way, you could see the back of your own head because light from behind you can circle the black hole and reach your eyes. But beyond this photon sphere, there's only one destination left. As you get this close to the singularity, even your own height begins to cause problems. The black hole pulls on different parts of you with different forces. If you were diving feet first into the black hole, your feet would be closer and thus pulled with much stronger force than your head, which is farther away. This difference in forces is called tidal forces. These tidal forces around the black hole start to stretch you rapidly, so much so that you begin to thin out like spaghetti. This horrific stretching is called spaghettification. The closer you get, the more you stretch until you're torn apart at the atomic level. However, if you want to experience a bit more action inside a black hole, entering one of the supermassive black holes like the one at our galaxy's center might be better. These giants, with masses at least 100,000 times that of the Sun, have much larger event horizons, so the gravitational well is much gentler at the edges. After crossing the event horizon, you could continue exploring the black hole's interior without immediate destruction due to gravity. Now, let's say you've found such a black hole and are approaching it. As you near, the black hole begins to engulf you and your field of view entirely. What would you experience upon entering this black hole? Nothing. This is one of the most common misconceptions about black holes. The event horizon isn't a physical object. It's just the point where light can no longer escape, appearing black to an outside observer, like the shadow of a wall. Contrary to popular belief, someone falling into a black hole wouldn't feel like they've entered a special void or a unique place in the universe. People think that once you cross the event horizon, you'd vanish or die instantly. That's not true. Depending on the size of the black hole, you could continue falling towards the center for minutes, hours, or even days under increasingly intense gravitational forces accelerating. But upon crossing the event horizon, you wouldn't feel any different. If you had a friend falling with you, you could continue chatting or even play table tennis as if nothing special had happened. Time wouldn't feel different to you. You'd continue on your way as if nothing had changed. The universe would shrink behind you until it became just a tiny point. However, an observer watching from outside would see a very different scenario. For them, you would approach the event horizon, but never quite reach it. Just as you were about to touch it, you'd appear to freeze. Remember, time doesn't just stop at light speed. In the context of gravitational time dilation, time also slows down near massive objects. At the event horizon, where time dilation is at its maximum, an observer would see time stop for you, hence you'd seem frozen. Also, as you approach the event horizon, your color would shift to red because the photons you emit would stretch increasingly before reaching an outside observer. At the point where you appear to freeze, you would slowly fade away because the photons would stretch beyond any detectable limit. Therefore, an outside observer could never see you actually enter the black hole. One of the most misunderstood aspects of relativity is this. While events in the universe might be agreed upon, how these events are experienced depends on the observer's speed and position. For you, falling into the black hole, you would genuinely fall in, not experiencing any freezing. But for the outside observer, you would indeed appear frozen at the event horizon. Both scenarios are simultaneously true. Time would continue to tick normally for both you and the observer, but for the observer, time would pass thousands of times faster than for you. Both experiences are real. Grasping this fully is tough, but if you want to understand how the universe works, you must challenge yourself to comprehend it. Anyway, once you've passed the event horizon, there's no turning back. No matter what you do, you can't escape. And this isn't about your speed. Even if you could go at light speed, you couldn't escape a black hole. The more you try to escape, the faster you get to the singularity, your end, because now, for you, space-time points only towards the singularity. If you want to maximize your time inside a black hole, there's only one thing you can do: stay completely still. Your fate is sealed. All directions and all times now lead to one place, the singularity believed to be at the heart of the black hole. Now, let me explain why I keep saying believed to be. Since we can't get information from inside black holes, we can only predict what's inside using the mathematical framework of general relativity. This isn't just any theory, it's one of the most accurate theories humanity has ever known, having passed every test thrown at it. For example, Einstein's theory predicted the existence and characteristics of black holes, but he was already dead when the first one was discovered. And we only managed to take the first picture of a black hole just 5 years ago. We're talking about a theory with tremendous predictive power. However, these equations suggest an infinite mass compressed into an infinitely small point at the center of black holes. Mathematics can predict something being infinite, but we've never encountered anything truly infinite in the physical world because math models an ideal world, whereas physics always deals with imperfections and approximations. Not everything mathematically predicted must be physically real. Remember, theoretical physics is largely about determining which mathematically possible scenarios are worth investigating experimentally. And in truth, very few believe there's an actual infinite singularity at the center of black holes. This is because Einstein's equations predict this singularity not due to an actual infinity, but because the equations of relativity start to break down at such an incredibly small point, much like how Newton's equations failed for Mercury's orbit around the Sun. Here, quantum mechanics, the science of small things, should come into play. However, no one has yet managed to reconcile quantum mechanics with Einstein's theory of relativity. Thus, we don't know precisely what we might find at the center of black holes. What are the alternatives? Some hypotheses suggest that this center bends spacetime so severely that it reconnects to another point in spacetime. This point would not be a black hole, but a hypothetical object called a white hole, spewing out everything swallowed by its connected black hole. According to this hypothesis, someone torn apart by a black hole could have their atoms spewed out from a white hole somewhere else in the universe. Unfortunately, there's no observational evidence for white holes. Some think black holes might be portals between different universes, as I'll discuss in upcoming videos. You could potentially travel from one universe to another through a black hole. But as you can see, all these wild ideas are just speculations. Relativity theory wonderfully predicts what happens until you reach the singularity, but what happens once you're there, we don't know. Maybe one of us needs to go there and see for themselves. What do you think? Here's the wildest and most thought-provoking fact about black holes. All black holes can be described by just three simple properties: mass, spin, or angular momentum, and electric charge. Black holes are almost always neutral, so let's skip that for now. That leaves just mass and spin. With these two properties, you can describe all existing black holes. Of course, these properties can take very different values in different black holes, but it's possible for multiple black holes to have identical mass and spin, and there's no known way to distinguish between two black holes that share these exact properties. There's something else in the universe that becomes indistinguishable when sharing the same values: subatomic particles. In other words, the most massive objects in the universe share a bizarre commonality with the smallest. What might this imply? We'll continue this discussion in upcoming videos. If you don't want to miss them, don't forget to turn on notifications now. See you in the next video. Goodbye.